Let us continue boron family. In the boron family, oxidation numbers we have to see. Now we'll take boron family elements: boron, aluminum, gallium, indium, thallium. These electronic configurations we know. Now thallium into thallium plus 1, that E naught. Thallium into thallium plus 1, that E naught we will take. That E naught is a plus 0.34 volt. Then thallium into thallium plus 3 will take, that E naught minus 1.26 volt. Minus 1.26 volt. Therefore, becoming thallus and becoming thallic. Becoming thallus, E naught is positive. Becoming thallic, E naught is negative. So from this we can say thallus is more stabler than thallic. Thallus TL plus. TL plus is more stable than thallic, TL plus 3 stability. Regarding, because inert pair effect, we said inert pair effect due to 4F14. Now we will see regarding indium. This indium into indium plus. Indium into indium plus. For that E naught. For that E naught is a plus 0.18 volt. Indium into indium plus 3. For that E naught is a plus 0.34 volt. Now you see indium plus 3 and indium plus 1, which is more stable? Indium plus 3 is more stable because plus 0.34 volt. Plus 0.34 volt. Here plus 3 converting into plus 3, E naught is more when compared to converting into plus 1. Therefore, we can say indium plus 1 is less stabler than indium plus 3. In the same way, gallium plus 1 is less stabler than gallium plus 3. Therefore, down the group, stability of plus 1 state, what happens means increases due to inert pair effect. Inert pair effect tendency increases. Why? Because here 4F14 very poor screening effect. Here 4D, here 3D. D shows a more screening effect when compared to F. Therefore, inert pair effect tendency is more in thallium when compared to indium. Due to more inert pair effect in thallium, plus 1 stability is more than plus 3. But in indium, plus 1 stability is less than plus 3. So down the group, inert pair effect tendency increases, we said. Therefore, stability will be like this. Then stability of plus 3. Stability of plus 3 decreases. Plus 3 stability decreases. Then what about minus 3 stability? Minus 3 stability. Minus 3 stability down the group decreases because electronegativity decreases. Electronegativity is decreasing down the group. Therefore, a minus 3 stability decreases. Now we will see electronegativity of these elements. Boron electronegativity is 2. Aluminum 1.5. Aluminum 1.5. Gallium 1.6. Gallium 1.6. Indium 1.7. Thallium 1.8. Thallium 1.8. You see the electronegativity. What we said here? Minus 3 stability decreases down the group because electronegativity decreases. Okay, see, boron to aluminum decreases. Then onwards, what happens? From aluminum onwards, increases by 0.1. Increases by 0.1 unit. Sorry. So remember that in the boron family, boron to aluminum, electronegativity decreases by 0.5. Aluminum to thallium increases by 0.1. Increases by 0.1 electronegativity. Next, we will see ionic radius of boron family elements. We will see. Now we will go for ionic radius. In the ionic radius, which oxidation number we are taking? Whether +1 oxidation number or +3 oxidation number. So, first we will take +1 oxidation number. Now boron +1 oxidation number, ionic radius we will see. For boron +1 not possible, therefore ionic radius not possible. Aluminum also +1 not possible. For gallium +1 possible, that ionic radius is 120 picometer. Then indium +1 is possible, that ionic radius is 140 picometer. Thallium +1 possible, that ionic radius is 150 picometer. 150 picometer. So from gallium to thallium, ionic radius of +1 increases. Then we will see +3 oxidation number. +3 oxidation number. For boron +3, ionic radius is 27 picometer. 27 picometer. Next, for aluminum 53.5. For gallium 62. Gallium 62. Indium 80. Indium 80. Thallium 88.5. So ionic radius increases down the group. There is no exceptional case here in the ionic radius in the +3 state. So now we have said about ionic radius. Next we will go for a melting point. Next we are going for melting point. How the melting point of these elements will be there, that we will see. Melting point of boron 2453 Kelvin. 2453 Kelvin. Melting point of boron. Aluminum 933 Kelvin. Then gallium 303 Kelvin. Gallium 303 Kelvin. Indium 430 Kelvin. Indium 430 Kelvin. Thallium 576 Kelvin. Thallium 576 Kelvin. Now we will see melting point. Melting point depends on what? Melting point mainly depends on structure, crystal structure. In the solid state, their arrangement. In the solid, they have certain arrangement. Based on that arrangement, melting point will be there. Sorry. Now, so in the melting point of these elements, let us see. The melting point of these elements and electronic configuration, that oxidation numbers, is there any relation? Melting point of elements and this oxidation numbers, any relation will be there? Yes. Based on oxidation number, valence electrons will be there, delocalized electrons will be there. Based on delocalized electrons, metallic bonding strength will be different, therefore melting point also will be different. Okay. So the number of delocalized electrons, one important factor. Next, crystal structures. Crystal structures, important factor. What is the crystal structures? That we will see. This boron comes under which case in the sense? It is a giant covalent polymer. Giant covalent polymer it is. Giant covalent polymer in the solid state. Which one? This boron. Polymer in the sense that will have continuous covalent bonds. Therefore, the melting point of boron is much high. Among these, actually boron is not a metal. It is a metalloid. Even then, its melting point is huge when compared to other elements of a group. Why? Because boron exists in the form of giant covalent polymer. Polymer in the sense continuous covalent bonds will be there between all the atoms. Between all the atoms, only covalent bonds are there. Therefore, breaking all the covalent bonds requires more energy. Therefore, the melting point is a huge one for boron when compared to other elements of a group. Okay. Next, what about other elements? Now, in the other elements, this aluminum face-centered cubic, otherwise cubic close packed structure. This indium distorted cubic close packed structure. This indium distorted cubic close packed structure. Indium. So this aluminum, gallium, indium coming under same crystal structure, FCC, face centered cubic or cubic close packed structure. Here if you see, down the group size increases. Aluminum to indium we are talking. Aluminum to indium size increases. Therefore, metallic bond strength decreases. Therefore, melting point decreases. Here, aluminum to gallium, metallic bond strength decreases because size is increasing. So, melting point decreases. They have same crystal structure. Distorted in the sense deviation from regular geometry. Some deviation from regularity. Okay. Aluminum comes under hexagonal close packed structure. In this thallium comes under hexagonal close packed structure, therefore different melting point. And also in thallium, inert pair effect is there, lanthanide contraction effect is there, that 4F14 is showing very poor screening effect. Because of that, metallic bond strength will be high. Therefore, your melting point is high. So in that gallium, this gallium shows a difference. In the aluminum, gallium, indium, if you see, gallium shows a difference. What is the difference? Means gallium shows much less melting point. Why gallium shows much less melting point? Means gallium exists in the form of discrete diatomic molecules. Discrete diatomic molecules, gallium. Gallium exists in the form of discrete diatomic molecules. That is, it is exist in the form of Ga2, Ga2, Ga2 like this. Now, in the Ga2, what will be there? In the gallium Ga2 diatomic molecule, what will be there? Means between two gallium atoms, covalent bond is there. Between two gallium atoms, covalent bond is there. Between Ga2, what is there? Here, just weak attraction is there. Here it is weak attraction, but it is strong attraction. Strong attraction. So, which is now here strong attraction is there. Here weak attraction is there. Therefore, breaking this attraction is easy. When you are converting solid into liquid, you have to make the greater distance here. That means you have to break this attraction. Since it is weak, we can easily break this attraction, isn't it? Therefore, this solid easily converting into liquid. So, melting point of this gallium is very low, we are seeing. So, why melting point of gallium is very low? Means it is a discrete diatomic molecule. It's a discrete word that indicates between this molecule and this molecule, the weak van der Waals force is there. That's why we are saying discrete. How we are saying in gas discrete like this? Between these two, between Ga2 and Ga2, there is no metallic bonding. So between Ga2 and Ga2, there is no metallic bonding. Here weak force is there. Therefore, only a melting point is low for gallium. Whereas for others are not discrete. Others are not discrete. That's why melting point is high. Okay. So how to say melting point in the sense? First, we have to consider metallic bonding. Metal in the sense metallic bonding. Intermolecular force of attraction. Then whether that is a metal or non-metal. Then crystal structure. All these factors we have to consider. Based on that only we can explain. So we have explained the melting point of these elements in this way. Next we will go for boiling point of these elements. We will go. How the boiling point will be there, that we will see. Boiling point of these elements. Now boron. Boron boiling point is 3923 Kelvin. Boron boiling point is 3923 Kelvin. Aluminum boiling point 2740. 2740. Gallium 2676. Indium 2353 Kelvin. Indium 2353 Kelvin. Thallium 1730 Kelvin. 1730 Kelvin. Now see the boiling point. Boiling point decreases down the group. Down the group, what happens to the boiling point in the sense decreases. Why? Because in the solid we can say crystal structure. In the liquid we cannot say. So crystal structure of these elements are different in the solid. Therefore melting point is different, we said. There is no gradual change. But boiling point, if you see, decreases down the group because crystal structures we cannot say for this. Therefore boiling point decreases down the group because down the group size increases. That's what we can say. Next we will see ionization enthalpy. Ionization enthalpy of these elements we will see. First we will take first ionization energy. First ionization energy, if we take boron 801 kilojoule per mole. 801 kilojoule per mole boron. Aluminum 577. Then gallium 579. Then indium 558. 558. Then thallium 589. Thallium. So down the group, what happens to the first ionization energy you see? Is there any irregularity? So boron to aluminum decreases. Gallium to indium decreases. So decreases means normal. Now we'll see aluminum to gallium. Instead of decrease, it is increasing. That is exceptional behavior as like atomic radius, because 3D10 present in the gallium, that shows poor screening effect. That's why ionization energy, first ionization energy shows exceptional behavior. Then indium to thallium, exceptional behavior. Indium to thallium ionization energy, first ionization energy, exceptional behavior, because in thallium 4F14 very poor screening effect. That's why. So we will see second ionization enthalpy. We will see. Now we will see second ionization enthalpy. In the boron family, we will see second ionization enthalpy. For boron 2427 kilojoule per mole. The second ionization enthalpy is greater than first ionization enthalpy. For whatever the element you take, for particular element, second ionization enthalpy will be greater than first ionization enthalpy. For aluminum 1816. For aluminum 1816. Gallium 1979. Indium 1820. Indium 1820. Thallium 1971. Thallium 1971. Thallium. So see the second ionization enthalpy and the corresponding first ionization enthalpy. Second will be more. Sir. Down the group of second, what happens? Boron to aluminum decreases. Gallium to indium decreases. Is there any exceptional behavior? Yes. Aluminum to gallium. Aluminum to gallium, what happens means increases, because in gallium 3D10 shows poor screening effect. Then indium to thallium increases, because in thallium 4F14 shows very poor screening effect. Therefore Next we will see third ionization enthalpy. Now boron we will take. Boron third ionization enthalpy is 3659 kilojoule per mole. For aluminum 2744. For gallium 2962. For indium 2704. For thallium 2877. See the third ionization enthalpy and corresponding second ionization enthalpy. Third ionization enthalpy will be more when compared to second ionization enthalpy. Okay. Down the group, is there any exceptional behavior that we see? Down the group, if you see, aluminum to gallium increases because in gallium 3D turn shows poor screening effect. Indium to thallium, we will see. Indium to thallium increases because in thallium 4 of 14 shows very poor screening effect. This is about ionization enthalpy in these elements. Okay, then how the density will be there, that we will see. How the density of these elements will be there. Boron density 2.35 gram per centimeter cube. (2.35 gram per centimeter cube). That is the density. Aluminum 2.70. 2.70. Next, gallium 5.9. Then indium 7.31. Then thallium 11.85. Now see the density of boron family elements. From boron to aluminum, what happens? See, boron to aluminum density decreases. Aluminum to thallium density increases, like electronegativity. In electronegativity, boron to aluminum decreases by 0.5. Aluminum to thallium increases by 0.1. Density, if you see, boron to aluminum increase, boron to aluminum, that means boron to aluminum not that means down the group increases. Down the group density increases. Boron to thallium, down the group density is increasing. Okay. Next we will see boron. Regarding boron, we will see how to prepare boron, that we will see. Boron exists in the form of isotopes. What are the isotopes means? B10 and B11. B10 isotope possible and B11 isotope is possible for boron. B10 isotope availability is 19%. B11 isotope availability is 81%. Now, occurrence of boron we will see. Occurrence of boron. One is called borax. Borax. Another name is tincol. Tincol. Its formula is Na2B4O7.NH2. Borax or tincol. Next, colemanite. Colemanite. Colemanite formula Ca2B6O11.5H2. Colemanite formula Ca2B6O11.5H2. Next, kernite. Kernite formula Na2B4O7.4H2O, kernite. Next, boric acid. Boric acid formula H3BO3. Boric acid formula H3BO3. Boric acid formula. Okay. So, boron can be extracted from these. From these, boron can be extracted. Now, how to extract boron from borax? That we'll see. From borax, how to extract boron? That method we'll see. First, borax should be treated with concentrated HCl or concentrated sulfuric acid. Okay, we'll take borax. We'll treat this with con HCl, otherwise con sulfuric acid. What will happen means this Na plus is replaced by H plus. Therefore, we are getting H2B4O7. H2B4O7. That means this Na plus and this H plus will be replaced. So we are getting a what means H2B4O7. Now, so in the borax, Na plus is replaced by H plus on treating with acid. So we are getting a H2B4O7. What is the name of this one means? It is called a tetraboric acid. This name is called a tetraboric acid. Then this sodium takes chloride and becomes sodium chloride. Otherwise, sodium takes sulfate and becomes sodium sulfate. Next, this tetraboric acid, H2B4O7, tetraboric acid undergoes hydrolysis to give orthoboric acid H3BO3. Orthoboric acid H3BO3. This H3BO3 is called orthoboric acid. Orthoboric acid. This orthoboric acid H3BO3 on strong heating gives boron trioxide B2O3 and water. This B2O3 on treating with sodium or potassium or magnesium gives boron. Sodium takes this oxygen and becomes sodium oxide. Potassium takes this oxygen and becomes potassium oxide. Magnesium takes this oxygen and becomes magnesium oxide. Now we will see how this borax is converting into tetraboric acid. How tetraboric acid is converting into orthoboric acid. Then how orthoboric acid is converting into B2O3. That we will see. First we will see borax. How the borax will be there. That we will see. Now borax formula Na2B4O7.10H2. Borax formula. In this borax, 4 boron atoms are there. So we will write 4 boron atoms like this. 7 oxygen atoms. Oxygen atoms present. Oxygen atoms we will write in between boron atoms. In between boron atoms we will write oxygen atoms. Let us write oxygen atoms in between boron atoms. Okay. We are writing oxygen atoms in between boron atoms. In between boron atoms, we are writing oxygen atoms. We have written. Sorry. Now, each boron is having 3 oxygen atoms. Next, we will write here OH group. We will write. We will write here OH group. We will write OH group here. OH group I have written. Now, this boron is having 3 bonds. This boron is having 4 bonds. Boron coming under group number 3A. Therefore, this valence shell contains 3 electrons, but it is having 4 bonds in the sense 8 electrons. That means for this gain of electrons, therefore for this we will give negative charge. This negative charge will be satisfied by Na plus. Okay. For this boron also 4 bonds, so we will give negative charge. This negative charge will be satisfied by Na plus. Now see, this boron is having how many oxygen bridges? 3 oxygen bridges for this boron. For this boron, how many oxygen bridges means 3 oxygen bridges. For this boron, 2 oxygen bridges, not 3 oxygen bridges. This boron is having 3 sigma bonds, so this valence shell is having 6 electrons. Therefore, it is not having any minus charge. This boron also is not having any minus charge. Sir. Next, we will count the oxygens. How many oxygens are there? That we will count. 1, 2, 3, 4, 5. 5 oxygens acting as bridges. How many OH groups? In the sense 4 OH groups, totally 9 oxygens. Out of 9, 7 is there. Remaining 2 take out from here. So remaining how many oxygens? Out of 10 means 8. Therefore, we will write 8 water molecules. Now we will check hydrogens. 20 hydrogens are there. Here 16 hydrogens. Remaining 4 is 4 OH groups. Therefore, 4 hydrogens, 20 hydrogens. Okay. Therefore, this borax, how to write this borax in the sense 2 Na plus ions. Therefore, Na2. Next, how many boron atoms in this one means 4 boron atoms. How many oxygen atoms present here? How many oxygen atoms present as bridges? How many oxygen atoms present as bridges means 1, 2, 3, 4, 5. 5 oxygen atoms acting as bridges. How many OH groups present means 4 OH groups present. Then how many water molecules? Hydrated water molecules 8. Therefore, this borax is what? Complex. This borax is a complex. It is not simple molecule. Okay, it is having complex structure. Therefore, borax formula, if we say borax formula in the sense one is simplified form Na2B4O7.10H2. Another one is complex form Na2B4O5OH 4 times 8H2. Now you say this is observation only, no? Observation means we should practice this one, then only we can remember the structures and formula of this borax and other chemical compounds. Okay. Now we came to know what is the formula of borax. Now, if we remove all the water molecules, how the borax will be there? That means here water molecules present. Because of water molecules, we have written structure like this. We are, suppose you think that we are heating this one, then all the water molecules will go away. Then what will be there? Na2B4O7 only will be there, isn't it? If you remove all the water molecules, all the 10 water molecules, if you remove, what will be there? Only Na2B4O7 will be there, isn't it? That is called anhydrous. Sorry. How to remove water molecules? One method by heating. Another method adding corn sulfuric acid. Corn sulfuric acid is having high affinity with water. That's why if it falls over our skin, it will absorb all the water molecules from the skin. Therefore, we will get a lot of burning sensation and the skin will be burnt off. That depends on quantity of corn sulfuric acid. So, corn sulfuric acid is having very high affinity with the water. Sir. Now, let us remove water molecules from here. Let us remove all these water molecules. All the 8 water molecules we are removing. Okay. All the 8 water molecules will be removed. Then you see that this OH group, this H plus will be removed as water. Okay. This OH takes this bond, and this hydrogen loses the bond. Therefore, now here you see that this borax we are heating. How many water molecules coming out we will see. From here 8 water molecules. Okay. Then you see this O takes this bond and becomes OH minus. This bond migrating towards this oxygen and becomes H plus, that hydrogen. Now this bond is migrating to oxygen, then it becomes H plus. This H plus and this OH minus becomes water. Okay. Then this similarly here this OH minus, this H plus becomes water. What is the remaining we will see. Now how many water molecules removed? Shall we say 10 water molecules? Here 8, here 1, here 1. So totally how much means 10 water molecules removed. Okay. Then what is the remaining you see? 4 boron atoms we will write. 4 boron atoms we have written. Between boron atoms oxygen linkage is there, oxygen bridge is there. We will write oxygen bridge between boron atoms, oxygen bridge. Then here this oxygen is there, it is not removed, that oxygen will write, that we will to write minus charge because this oxygen takes the bond. Similarly this oxygen takes the bond, therefore O minus will write. This boron is having negative charge, this boron loses this bond, therefore negative charge will be vanished off, therefore just boron will be there. This negative charge is satisfied by Na plus, here also Na plus. It is called Na2B4O7. Okay. So Na2B4O7 is this one. Okay. So we have written Na2B4O7 we have written. Let us add acid into this. Acid will give H plus. Na plus will be replaced by H plus. Okay. To this we are adding corn HCl, otherwise corn sulfuric acid. Corn sulfuric acid and corn HCl will donate H plus. Now H plus and Na plus will replace its place. So in this place what is coming means H plus coming, Na plus going away. Here also H plus is coming. So H plus comes in the sense how the structure will be there. We will see the structure will become like this. Here instead of Na plus we are writing H plus. Okay, we got like this. This is only called a tetraboric acid. This name we are calling as a tetraboric acid. This tetraboric acid undergo hydrolysis to give orthoboric acid. How hydrolysis takes place, that we will see. Now we will take this boron. This boron electronic configuration is helium 2s2 2p1. So 2s contains 2 electrons, 2p contain 1 electron. It is ground state configuration. Excited state means from 2s 1 electron goes to 2p. From 2s 1 electron goes to 2p. Okay. Now one vacant orbital is there. This boron is making 3 bonds with these 3 electrons. Okay. This boron is making 3 bonds with these 3 unpaired electrons.